Hello everyone. My name is Maria Wirzberger. I'm an assistant professor for teaching and learning with intelligent systems at the University of Stuttgart, and I'm going to introduce you to the concept of cognitive load in instructional design. As we all know, learning is an omnipresent lifelong experience that is particularly demanding when we try to acquire something completely new. To build educational technologies that support learners in this process in the best possible way, we need to understand the underlying cognitive dynamics. My ongoing work in this field uses behavioral experiments and cognitive modeling to inspect learners' cognitive resource demands on the behavioral and neural level. Theoretically, I focus on the cognitive load theory by John Sweller and colleagues, which is a well-established framework in multimedia learning research. It deals with the question to what extent selected aspects in learning scenarios demand learners' cognitive resources. A core assumption in this theory is that learning is impaired when the total amount of processing requirements exceeds the limited capacity of human working memory. Long-term memory resources provide a nearly infinite storage capacity and can be used to establish organized knowledge structures permanently. These knowledge structures are called schemata. The theory also postulates distinct facets of cognitive load that arise from certain characteristics in learning situations. Intrinsic cognitive load relates to the complexity of the used learning material in relation to existing previous knowledge. It involves the concept of element interactivity, which is defined by the number of logically interrelated information units in learning material. Extraneous cognitive load refers to harmful effects of task-irrelevant features, such as an overly complex instructional presentation or competing goals from an interrupting task. Germane cognitive load is related to establishing and refining knowledge structures in long-term memory, which is referred to as schema acquisition and automation. In my existing research, I used basic experimental task paradigms like the displayed symbol sequence learning task to inspect the interplay of the introduced cognitive load facets in a very controlled manner. For example, I manipulated element interactivity by selectively increasing or reducing the number of symbols in a defined order, or I embedded an interrupting visual search task to introduce additional situational constraints. To connect the conceptual framework of the cognitive load theory directly to mechanisms of human learning, I used a well-established formal modeling approach, the cognitive architecture ACT-R. ACT-R is particularly characterized by its modular brain-inspired structure, which you can see in the graph. The included modules represent goal planning, declarative memory, intermediate representations, action coordination, visual and auditory input, and motor and vocal output. Buffers serve as an interface between these modules, and while processes in different modules can be executed in parallel, each module can only process one information element at the same time. These information elements are called chunks. The interaction between these modules happens via production rules that define the model's behavior. They look like this and consist of a condition part and an action part. If the requirements in the condition part are fulfilled, meaning the modules have a certain state or content, the model performs the related action. In this example, the goal was to retrieve a product from a memorized shopping list, which has not been successful, so the model looks for content on the screen instead to cope with the situation. In this video, you can see an ACT-R model performing the symbol sequence learning task that I have shown you earlier. As the possibilities of ACT-R's experimental interface are quite limited, the symbols are represented as text. At a certain point, an interrupting visual search task is executed, with different symbols being represented as text in different colors. The red circle indicates which of the items in ACT-R's visual world is currently in focus. All visual information that the model could access is shown in the bigger window in the background at the upper left corner. The smaller windows on the left side offer a view inside the modules. For example, you can see in the bottom left window if information could be retrieved from declarative memory. In the middle left window, you can see which task goal is currently active. You can also keep track of intermediate representations when multiple symbols have to be memorized one after another, which you can see in the topmost left window. Characteristically, ACT-R uses a hybrid approach of both symbolic and subsymbolic mechanisms, meaning chunks of information from declarative memory are retrieved not only on the match in their slots, but also based on their level of activation, which is outlined in this equation. The higher the activation, the faster and more accurate information can be retrieved. Activation is calculated from the history and context of use of a chunk, and it has to exceed a defined threshold that a chunk can be selected. It consists of several components. The base level activation represents the recency and frequency of use, and it decays if a chunk is not used. The spreading activation mechanism accounts for the influence of the current context on information retrieval. For example, if similar symbol combinations are present, they might be confused with each other. The partial matching mechanism penalizes the retrieval of related but ultimately wrong information. Also, a noise parameter is computed for each retrieval request. Since all of ACT-R's modules have been linked to certain brain regions, ACT-R can also be used to predict brain activity. For example, when a model retrieves information from declarative memory, the increased activity in the declarative module corresponds to increased activity in a region around the inferior frontal gyrus in the prefrontal cortex, which is displayed by the pink squares in the graph. This area has proven sensitivity to both retrieval and storage operations. We can now record when the modules are active and represent these times as 0-1 demand function. The result can then be convolved with a hemodynamic response function to simulate a signal that is comparable to the blood oxygenation level from fMRI. Referring back to the activation equation, lower levels of chunk activation in declarative memory would result in longer retrieval times, which would then be observable by higher peaks in the simulated fMRI signal. This is displayed in the graph, which shows you the simulated neural response patterns for the prefrontal cortex. The solid lines represent an easier task condition with fewer symbols per combination. The dashed lines represent a more complex task condition with more symbols per combination. Blue lines relate to the early stage in the task, red lines relate to the intermediate stage, and black lines relate to the late stage. With more frequent use, chunk activation increases over time, and this results in increasingly faster retrievals. This is obvious by lower peaks in later stages. In the more complex condition, retrieval times are always longer. This relates to the higher potential of retrieving a wrong information related to the symbol order, which would penalize the chunk activation. From the simulated brain activity patterns, we can predict less effortful information access with increasingly established knowledge structures, as well as an overall increased level of cognitive load in more complex task conditions. The next step in this ongoing line of research will be to validate these simulated brain response patterns with actual human brain data and potentially refine the existing models. In the mid and long term, I would like to further explore potential connections of ACT-R with the cognitive load theory, and I'm particularly interested in a conceptual framework for exploring facets of cognitive load with fMRI that has been outlined by Robert Whelan. It postulates that changes in intrinsic cognitive load would manifest themselves in the dorsolateral prefrontal cortex, because this area mediates attentional maintenance and manipulation. Extraneous cognitive load should be observable in the parietal cortex and Broca's and Wernicke's areas, which involve modality-specific neural structures. Germane cognitive load would be associated with activity in brain structures underlying motivation, particularly the superior frontal and intraparietal sulcus. This potential correspondence emerges as learners need to be motivated to invest cognitive resources in building knowledge structures. In addition, the concept of element interactivity could be reflected in the mechanism of spreading activation, because this increases the effort of retrieving the correct information with increasing connections between information elements. With that, I would like to thank my collaborators and the funding agencies for supporting the outlined research. And I would like to thank you for your attention. Now, I'm happy to answer any questions that you might have.